If it doesn't refresh, because I had that same problem with Synergy, you can just go. Yeah. All right. I get your attention up front, please. Today we're talking about systems of linear equations. So equations in two variables, x and y equals mx plus b, or something that is equivalent to that expression. And a solution to a system of two or more linear equations is the set of all points that satisfy each equation independently. That's the big fancy formal pre-cal definition. In other words, slightly less scary words, the solution to a system of linear equations is where all of the lines intersect in a graph. Where do they cross? Where do they touch? The solution to a system of linear equations is the point or set of points that all of the lines have in common. So where do they overlap in the graph? And there's three possible outcomes when I'm plotting just two equations, and we're going to focus on solving systems of two. If I'm plotting just two equations, I have three options. The first is that my system has exactly one solution. There is one point in common. The lines only cross at one point. We saw that in our bell ringer today. I had one line that tilted up. I had one line that tilted down. They crossed exactly once here, and that's my solution. You will notice that that point on a graph represents two values, an x value and a y value. A solution, or solutions, to a system of equations are ordered pairs, x and y. Second possibility is that my system has no solution. If the solution to my system is where the lines cross in a graph, what would a graph look like with no solution? Yes, Vicky's doing this. Very good. Those lines would be parallel. They're never going to cross. I'm not very good at drawing, apparently. But these lines are parallel. I think I spelled that right. And lines that are parallel have the same slope. So if I am looking at a system of equations that are written in slope-intercept form, and I see the same slope, but different y-intercepts, I know that I'm here without having to do any math. Because lines that have different intercepts, but have the same tilt, are never going to cross. And then the last one. They cross once, they don't cross at all, or they are exactly the same line, same slope and same intercept. If that happens, you have infinitely many solutions because the lines are the same line. So a system that has infinitely many solutions, those equations are the same equation written in different forms or off by a single constant, like I've multiplied everything by 2, which divides out. You will notice that there's some new vocab words above those graphs. If a system of two linear equations has one solution, we say that they are independent. Independent. Meaning the behavior of y for the first line has nothing to do with the behavior of y of the second line. Different tilts, different systems. If a system has no solution, we say it is an inconsistent solution. If they overlap, meaning they plot the same line, we call it a dependent system. If I know what's happening to y for one of those lines, I know what's happening to y for the other. They are dependent. They are connected. Good. So what we're going to talk about is the three methods that we learned for solving systems of linear equations. So review. We'll start with the one that we did in the bell ringer, which is solving by graphing. Finding that intersection by graphing. So we're going to walk through what we did with our bell ringer. And the first thing is we need to check that those equations are written in a form that's easy to graph from. The equations they gave you in the bell ringer were already in this form. What form were those equations in? Slope-intercept. Good. Yeah, we want them in slope-intercept form. So if you are asked to graph, put them in slope-intercept form. If you are given equations that are all in slope-intercept form, graphing might be a good place to start. So once we've done that, we're going to graph each line on the same graph. And we know how to graph from slope-intercept form. First, plot the intercept on the y-axis. Use your slope to find your second point. Play connect the dots. Yeah, we did it for our bell ringer. You have to draw both lines on the same graph because what we are looking for are points of intersection. Where do they cross? Where do the lines overlap? You should state that ordered pair if it's one solution. You should state infinitely many if there's overlap for both lines. They're the same line. You should state no solution if they are parallel and they never cross. You should also identify the system as independent, inconsistent, or dependent. Meaning you need to remember independent means one solution. Inconsistent means no solution. Dependent means infinitely many. Infinitely many. Why is writing so hard today? I don't know. Write them in slope-intercept form, slap them on a graph, identify where they intersect, identify them as independent, inconsistent, or dependent. We're going to see some examples, and then we'll move on to the next method of solution. So first one says solve by graphing. They give us the equation y equals 1/2 x plus 1 and y equals 1/4 x minus 2. Are these lines parallel? Luna's shaking his head no. How do you know, Luna? You already graphed it. Luna's a speedy grapher. Somebody who hasn't graphed it yet. How can we tell that Luna's correct? Yes, Vicky. Very good. Different slopes, 1/2 and 1/4. So I know they tilt at different rates. One is steeper than the other. So at some point they have to cross. Good. So we're going to graph. I'm going to do the first one in red, and I'll do the second one in blue so I can keep them track. First one, I start with the y-intercept, which is what? 1. So go up to 1. And then I use the slope. Slope is actually negative 1/2. I couldn't see. Yeah. Couldn't see the negative. Negative 1/2. So down 1, forward 2. Down 1, forward 2. And play connect the dots. Maybe. Did I do that correctly? Get some nodding. Okay. And the second one. Who can tell me where the y-intercept for my second line is? -2. Very good. And then it's positive 1/4. So up 1, forward 4. Up 1, 1, 2, 3, 4. I can already see my intersection point. That's kind of nice. So my intersection point is right here. And the ordered pair for that is 4, -1. And based on the number of solutions that we have, is this independent, inconsistent, or dependent? Independent. One solution means independent. Good. Perfect. Solution of 4, -1, system is independent. Perfect. All right, there's another example on the next page. I'm going to give you about 2 minutes. I want you to do it in your small groups. And then I'm going to have somebody either come up to the board or walk me through it. Why is your mom text messaging you in the middle of pre-calc class? I'm sorry. All right. I need a volunteer who either wants to come graph or walk me through how to graph. Preferably somebody who hasn't spoken yet today. Can I get a volunteer? Oh, frowny face. Frowny face. Hey, Jesus. How should I start graphing that first equation? You think we should start at -2? Okay. One, 2, 3, 4, 5. Okay. And then back 1, 2, 3, 4. And you did a line. I like that you were resourceful and you thought to work backwards because it wouldn't fit off the graph going forwards. And I'm pretty sure you did that correctly because I know if my slope's negative, the line should tilt down. And this line does tilt down. Very good. Very good. You think Jonathan should do the next line? Okay. You've been thrown under the bus by your friend. 2 on the y-axis. Okay. We could go up 1 and back 4. Or we could go down 1 and forward 4. Either of those. Good. Oops. And we can see where our intersection point is. So this line intersects at, and what are the coordinates of that point? -4, 3. Good. So we have one solution at -4, 3, which means this system is independent. Very good. Excellent. Doable. We remember how to graph lines. Our calculator can do the same thing. You can put both lines in the y equals menu and then graph it. And then your calculator can find the intersection point. Yeah? The downside is that sometimes those lines will not cross at a grid point, which means you can't find an exact answer from the graph. And in those cases, we try one of two other methods. The first being substitution. We use substitution when at least one of the equations has already been solved for one of the variables, meaning it's in slope-intercept form, we solved for y, or it's been solved for x, x is by itself. But to use substitution in one or more of the equations, I have to have a variable by itself. And what we do is we take that equation, we substitute it into the other equation. So we're going to do two examples to review. First example, we have the system -5x minus 7y equals 12, and y equals 2x plus 20. And I want to solve by substitution. And I see my second equation is in slope-intercept form. It has y by itself. And that second equation tells me that y is equal to 2x plus 20. Everywhere in the top equation, the one that I haven't touched in red, where I see a y, I am going to replace it with its definition, 2x plus 20. So this is going to get replaced by the thing below it. All right, so let's bring that equation down. I've got -5x minus 7y equals 12. I'm going to replace y with 2x plus 20. Notice that everything else about that top equation is the same, but I've replaced y with parentheses because I'm going to substitute in for y. And then I write the thing I'm substituting in for, which is 2x plus 20. I like that as a mathematician because now I only have x's floating around. I can solve for x. Suggestions on what I should do first. Distribute, very good. I got to get rid of those parentheses. Distribute the 7 through. So I have -5x. -7 times 2 is -14x. -7 times 20 is 140. I think I did that correctly. 7 times 2 is 14 plus a 0, yeah? Equals 12. Next suggestion. What am I adding? Combine like terms. Very good. There's an x term and an x term. So -5, -14 becomes -19x. Minus 140 equals 12. Now I want to get x by itself. I'm going to add 140 to both sides. So -19x equals 152. Right? 12 plus 140. Good. Last step. Divide the constant out in front of the x, divide by its coefficient, so divide by -19. Somebody with a calculator. -8. Perfect. Am I done with the problem? I see shaking head no. What else do I need to find? Y. I need to find y. And typically what I will do, off to the side, is I'll go back to the equation that has y by itself and plug this value into the second equation. So I am going to take x equals -8 and substitute it in up here. So y equals 2x plus 20. I now know that x is equal to 8. 2 times 8 is 16. 16 plus 20 is 36. Was it -8? It was -8. So -8, -16, 4. Thank you. 4. So my solution is at -8, 4. I can box that and be happy. And since I got one single point, my system is independent, inconsistent, or dependent? Independent. Very good. Happy face. Okay. Move sideways. The next one. We're going to do the same thing. Alex, what should I do first? Very good. Very good, because we have y isolated here. So 7x plus 5y equals 13. And everywhere I see a y, it becomes that expression. So -2x plus 2. Good. Ethan, what do I do next? Very good. Get rid of the parentheses. 7x minus 10x plus 10 equals 13. I think I did that correctly. I see some nodding. Combine like terms. So 7 minus 10 is minus 3x plus 10 equals 13. I'm going to subtract 10 from both sides. -3x equals 3. I'm going to divide by -3. X equals -1. I think I did that correctly. And the question is, where do I go next? Junaidi, what do I do next? Very good. So we go back to the equation we haven't used yet, y equals -2x plus 2, and we substitute in -1. So y equals -2 times -1 plus 2. And negative times negative becomes positive. So y equals 4. So the solution to this system is -1, 4. And this system is also independent. Very good, because it's one solution. It's independent. Good. Again, hopefully feels vaguely familiar now that we're seeing it. We've done it before. There is one more method. What is our last method? Elimination. Very good. Everybody's favorite. Okay. So Last method is the method that connects to the method we're going to introduce tomorrow. It's related to the new method. And the idea with elimination is we're going to combine the two equations into a single equation by adding or subtracting in such a way that one of the two variables cancels out, either the x or the y. Thus the elimination. The first step is we look at our equation and we are looking for matching coefficients. So I check the x's, do the numbers in front match? I check the y's, do the numbers in front match? I want matching coefficients on one of the variables. If I don't see any matching coefficients, I am going to multiply one or more of the equations by a constant, by a number, so that the coefficients of one of the variables does match. If the variables don't match, they won't cancel when I add or subtract. I need matching coefficients on one of my variables. So once I have my equation set up so that one of the coefficients matches, I'm going to add or subtract the equations so that the variable with the matching coefficients cancels out. If the matching coefficients have the same sign, I should subtract, s with s. If the matching coefficients have opposite signs, I add. I want to do whatever operation gets them to cancel out. And once I've done that, I'm going to solve for the variable that's left over. And it's usually 2 steps. Add a constant to both sides, divide by some stuff, not too bad. Just like the substitution method, once I have found one variable, I have to go back to my original equations and substitute it in to find the other. So elimination is first step elimination, second step substitution. We're going to do a whole bunch of these examples. We'll get started today. That what we don't finish, we'll do for a warm-up tomorrow. Yeah? Okay. Are all the examples on the next page? Yes, they are. Okay, so first example. We have the system 4x minus 9y equals 3 and 4x minus 4y equals 8. And first thing I look for when it says solve by elimination is, do I have matching coefficients on one of my variables? Yes. The x's both have 4s, so I don't need to multiply by anything. The next question is, do I add or subtract? And I hear subtract. Good, they have the same sign. If I added 4 plus 4 is 8, that wouldn't cancel. So I need to subtract when I do this math. And you need to remember that you are subtracting the whole bottom from the top. You're subtracting by term. So we're going to go down this list and do that. So 4x minus 4x gives me 0. Yeah, anything minus itself is 0. Negative 9 minus a minus 4 is negative 5. Negative 9 minus minus becomes plus. So this is negative 9 plus 4, which is negative 5y equals, and then 3 minus 8. 3 minus 8 is negative 5. Good. I want to solve that for y. I can ignore the 0. What should I do? Divide by negative 5. Yeah. Divide by negative 5. Divide by negative 5. I get y equals 1. I am not, unfortunately, done. I am halfway done. The next step is to pick one of my original equations, substitute in y as 1, and solve for x. So I only have half of my ordered pair. I need the other half. It doesn't matter which of the equations you use. We can pick either. Does anyone have a preference? No. So I'm going to use the first one because I'm lazy and it's the first one I see. So 4x minus 9y equals 3. Everywhere I see a y, it becomes a 1. 9 times 1 is 9. So 4x minus 9 equals 3. Oh, and what should I do next? Plus 9 to both sides. So 4x equals 12, assuming I can do addition in my head. Bella, last step. Perfect. Divide out the coefficient on the x. So x equals 3. I think I did that correctly. So our solution is the point 3, 1. Yay. Independent, inconsistent, dependent. Independent. Good. Questions on the first one? No, feels vaguely familiar, tickling the back of our brain. We've seen it before. Try another one. Next one. 3x minus y equals 9. Negative 4x plus y equals negative 10. First question. Anela, are there a pair of matching coefficients up there? You're nodding. I agree. The y's match. The next question is, do I add or subtract? Allie, add or subtract here? Add. Very good. Opposite signs we add. And plus my minus y, I just add to get them to cancel. So, plus all the way across. 3 plus a negative 4 is a negative 1, so negative x. Minus y plus y is 0. 9 plus a negative 10 is a negative 1. So this is negative x equals negative 1, which means x equals 1. Divide both sides by negative 1. Yeah. Good. Lupe, next step. Very good. And I like the use of mathematical vocabulary. We're substituting into one of the original equations. I'm going to go with the top because I'm lazy. So 3x minus y equals 9. And I now know x is 1. Correct me if I'm wrong. I think I did that correctly. Next step, suggestions. Minus 3. Very good. So that the 3's will cancel. I get negative y equals 6. I don't want negative y. I want positive y. Divide by negative 1. Yeah. I don't know why I did that in black. So y equals negative 6. I agree. Yay. Solution is 1 comma negative 6. Yeah. Perfect. Before we do the last one, you'll notice some patterns. When I did graphing, both my equations were in slope-intercept form. That's a good place to start. When I did substitution, one of my equations was in slope-intercept form. When I'm doing elimination, none of my equations are slope-intercept form. Everything's in standard form. So generally, When I have to choose between those three methods and I'm not told to use one of them specifically, the way the equations are written dictates which one I choose. So if they're both in standard form, it's easier to do elimination because then I don't have to rewrite them in slope-intercept form. All right, another example. Negative 7x minus 5y equals negative 11. Negative 2x plus y equals negative 25. Are there any matching coefficients? No. I cannot turn 2 into 7. Nothing times 2, that's a whole number, will make it 7. Meaning I would have to multiply both equations by a number if I wanted the x's to match. So I'm going to focus on the y's. I have a 5y and a 1y. What should I multiply the bottom equation by? 5. Yeah, much easier. I'm going to modify the bottom equation only, and I'm going to multiply it by 5. So I'm going to rewrite my system. I have negative 7x minus 5y equals negative 11. And then the second equation, everything's times 5. So negative 2 times 5 is negative 10x. And then plus 5y. And then minus 125. Y's match. Do I add or subtract? Candy, add or subtract here? Why? So what is negative 5y minus 5y? It's negative 10y. Yeah. So we only subtract when the signs are the same. The signs are different, we want to add. So I'm going to add, because negative 5 plus 5 will give me 0. So starting with the x's, negative 7 plus negative 10 is negative 17. Yes. Negative 5 plus 5 is 0. Negative 11 plus negative 125 is negative 136. I think I did that correctly. So I'm going to divide both sides by the negative 17. And somebody with a calculator, what is negative 136 divided by negative 17? 8? I see some nodding. Positive 8. So x is positive 8. Perfect. Next step. Emiliano, what do I do next? So negative 7x minus 5y equals negative 11. Everywhere I see an x, it becomes an 8. In other words, we're substituting. Very good. Substituting that answer into the first equation. 8 times 7, 56. Yes, okay, thank you. So negative 56 minus 5y equals negative 1. So I'm going to add 56 to both sides. Huh? Oh, it is negative 11. Thank you. Thank you, Vicky. So 56 will cancel negative 5y. And negative 11 plus 56 is 45. Yeah. And then I'm going to divide by the coefficient on the y, so divide by negative 5. So y equals negative 9. 8. Thank you. Is it 8? No, it's 9. It's 9, right? Yeah. Because 10 would be 50. Yeah. So our solution is 8, comma, negative 9. Happy face. Happy face. I am hoping, again, that feels familiar. There's a little bit of that in your Delta math for this week. First couple questions. The elimination method, this process where we're multiplying equations by a constant and then adding or subtracting them to the other equation, relates to what we're going to start talking about tomorrow. Starting tomorrow, we're going to learn about matrices and how to solve systems of equations using matrices. How many people have seen matrices before? Do we know what a matrix is? Anyone? No, completely new math. Yay! So tomorrow we'll introduce matrices. We'll start looking about how to use them to solve systems of equations. It'll be fun. Yay!